The Dream Chaser is being designed. It could rendezvous with any space station and then fly back to a runway landing. It's just incredible how much of a leap forward in technology it is compared to what the shuttle was.
What if NASA never truly needed to leave winged spaceflight behind? After years of watching capsules splash into oceans and parachutes drift through the sky, something unexpected is landing, literally, on the runway again. But this isn't about nostalgia or rehashing the shuttle's troubled legacy. A new player is bringing a radically rethought design that claims to fix what no capsule ever could. And while SpaceX's Dragon redefined reliability in orbit, it may have hit a wall that this new approach intends to break. One specific capability, once dismissed as too complex, might now be the linchpin for a faster, smarter return from space. Curious? You should be. The return of the spaceplane. The idea of a reusable winged spacecraft isn't new. NASA's Space Shuttle embodied it for over 3 decades. First launched in 1981, the shuttle could transport both crew and cargo to low Earth orbit and return with runway landings. It introduced the concept of large payload bays, gliding re-entry, and rapid reuse, at least in theory. But the shuttle's promise was undercut by extreme complexity and high operational costs. 2 catastrophic failures, Challenger in 1986 and Columbia in 2003, exposed its safety shortcomings. With over 24,000 heat shield tiles, volatile launch configurations, and intensive turnaround requirements, the shuttle was ultimately retired in 2011, leaving NASA and its partners with only capsules as practical transport systems. Sierra Space, a Louisville-based aerospace company, has taken up the challenge of reinventing the spaceplane model with a modernized approach. Their flagship vehicle, Dream Chaser, is a sleek, compact craft designed to leverage the benefits of a gliding winged re-entry while addressing the operational and safety flaws that plagued the shuttle. Unlike its predecessor, Dream Chaser is smaller, simpler, and engineered from the start for frequent reuse and affordability. Its return to a runway landing, not a splashdown, offers gentler deceleration, which is ideal for sensitive science cargo and potentially for future human passengers. The vehicle is also designed to be more modular and compatible with today's commercial launch infrastructure. The capsules, such as SpaceX's Dragon and Boeing's Starliner, became the obvious choice after the shuttle was retired, providing a safer and cheaper transport to space. Their blunt body design has made heat shielding for re-entry much easier, while concurrently simplifying the mechanical design. However, there are limitations to the capsules. They land either in oceans or in deserts, making recovery even more difficult and hazardous for delicate cargo. Further, capsules fail spectacularly to accomplish quick reusability as the concept scarcely scales. And this is where the Dream Chaser starts re-establishing the debate and bridges the reliability of capsules with winged vehicles' operational flexibility. Sierra Space, going back to Dream Chaser, is not a nostalgia trip. It's strategic. In a world dominated by capsules, this vehicle type offers some alternative architecture to tackle long-standing constraints in contemporary space logistics. Could it be that wings are the next great paradigm shift for spaceflight, but this time done right? Suddenly, the spotlight shifts from design ambition to a real-world mission that could quietly rewrite how NASA keeps the ISS stocked and science flowing. Tenacity's mission profile. Tenacity, the first operational Dream Chaser vehicle, is set to join NASA's Commercial Resupply Services 2 (CRS-2) program, a critical logistics initiative supporting the International Space Station (ISS). Under this contract, Sierra Space is scheduled to complete a minimum of 7 uncrewed cargo missions to the ISS, joining SpaceX's Cargo Dragon and Northrop Grumman's Cygnus as the 3rd provider. The CRS-2 contract ensures uninterrupted delivery of food, science payloads, and station hardware, marking Dream Chaser's entry into active duty within NASA's orbital supply chain. This contract reflects NASA's increasing willingness to diversify its cargo transportation capabilities through partnerships with private industry. While Cygnus and Cargo Dragon have proven reliable in their respective roles, Dream Chaser introduces a unique capability to the fleet: runway landings. Both Cygnus and Cargo Dragon deliver cargo effectively, but their return strategies differ. Cygnus burns up on re-entry, offering no downmass return capability, while Cargo Dragon splashes down in the ocean, requiring time-consuming marine recovery. Dream Chaser, in contrast, will land on a runway, offering a gentler return that is particularly beneficial for sensitive biological experiments, delicate instruments, and time-critical samples. This expands NASA's operational flexibility by adding a vehicle optimized for rapid return-to-lab logistics, a key advantage for scientific missions. Sierra Space has confirmed that Dream Chaser's first mission will deliver over 3,500 kilograms, about 7,800 pounds, of cargo to the ISS. The Shooting Star cargo module, which attaches to Dream Chaser, enhances total delivery capacity and includes both pressurized and unpressurized sections. The length of each mission is expected to vary, with plans for Tenacity to remain docked to the ISS between 30 and 90 days, depending on NASA's scheduling needs. Following undocking, Dream Chaser will re-enter Earth's atmosphere and touch down at the Kennedy Space Center's former Shuttle landing facility. A return to runway landings not seen since the Shuttle era ended in 2011. Tenacity is currently completing final environmental and integration testing at Kennedy Space Center, with a launch target of no earlier than mid-2025 atop ULA's Vulcan Centaur rocket. Sierra Space's performance on these early CRS-2 missions will likely influence future NASA contracting decisions. If successful, could Dream Chaser set a new standard for orbital cargo return, one that blends commercial innovation with shuttle-era capabilities, but with 21st century reliability? Engineering for flexibility. One of Dream Chaser's most forward-looking features is its launch vehicle agnostic design, meaning it can be integrated with various rockets that meet the minimum size and payload fairing specifications. This is a strategic departure from legacy spacecraft like the Space Shuttle, which required a custom-built launch stack, and even from modern capsules like Dragon, which are tightly integrated with specific rockets. Dream Chaser's compatibility with multiple heavy-lift vehicles, particularly those with 5-meter fairings, ensures Sierra Space is not dependent on a single launch provider. This design flexibility is not just about convenience. It significantly reduces operational risk and increases launch availability. For its debut missions, Dream Chaser will launch aboard United Launch Alliance's ULA Vulcan Centaur rocket, specifically the 542 variant. This version features a 5-meter payload fairing, 4 solid rocket boosters, and a dual-engine Centaur upper stage, making it suitable for Dream Chaser's cargo mass and dimensions. The choice of Vulcan reflects both technical compatibility and strategic alignment. Vulcan is designed to replace ULA's Atlas V, which had been a staple for many government and commercial missions. Should the need arise in the future, Dream Chaser could be adapted to fly aboard other vehicles with similar fairing dimensions, such as SpaceX's Falcon 9, Blue Origin's New Glenn, or even Arianespace's Ariane 6. This multi-launcher approach provides Dream Chaser with resilience in the face of delays, launch failures, or scheduling conflicts that could affect a specific rocket family. For NASA and other commercial partners, this translates into a more reliable delivery cadence and the ability to adjust launch logistics without re-engineering the spacecraft. In contrast, vehicles tightly bound to proprietary launch systems often face bottlenecks if issues arise in the rocket's supply chain or flight manifest. In an increasingly dynamic launch market, having a spacecraft that can move across platforms is a competitive advantage. Dream Chaser's fairing-encased launch configuration also contributes to pre-launch protection, reducing the risk of damage from debris or weather, a known problem with the shuttle's exposed external tank. This setup not only safeguards the vehicle's thermal protection tiles during ascent, but also simplifies integration and testing workflows at launch sites. Looking ahead, could this modular, adaptable philosophy be the blueprint for next-gen spacecraft across the industry? If launch infrastructure continues to diversify, Dream Chaser's flexibility might become more of a necessity than a novelty. The Dream Chaser Shooting Star Duo. A key component of Dream Chaser's mission capability is its companion module, Shooting Star, a versatile cargo system that attaches to the rear of the spaceplane. This module is not merely an add-on, but a core part of the overall design, enabling Dream Chaser to handle a wide variety of mission payloads. Shooting Star expands the spacecraft's total volume and payload mass, allowing for both pressurized and unpressurized cargo delivery to the International Space Station, ISS. This modular approach is central to Sierra Space's logistics strategy, giving NASA and future customers a more flexible and customizable transport solution. The design allows Dream Chaser to carry up to 5,500 kilograms of total cargo, substantially more than what the base vehicle could accommodate on its own. The pressurized section of Shooting Star holds critical items like food, medical supplies, and delicate scientific experiments, while the unpressurized section is ideal for hardware or external payloads that don't require a controlled environment. Once docked at the ISS, Shooting Star can stay attached and serve as an additional storage platform before being jettisoned to burn up in Earth's atmosphere, similar to the disposal function of Cygnus. Sierra Space has declared that Dream Chaser's first mission will ferry over 3,500 kilograms, approximately 7,800 pounds, of freight to the ISS. The Shooting Star cargo module, which attaches to Dream Chaser, adds to the delivery ability by providing room for pressurized and unpressurized cargo. The length of each of the missions will vary, with Tenacity expected to dock at the ISS for 30-90 days, depending on NASA's scheduling requirements. After its mission, Dream Chaser will leave the docking port of the ISS, get back to the atmospheric plane, and land on the historic Shuttle landing facility at the Kennedy Space Center, marking its return to runway landings after the shuttle operations ended in 2011. Tenacity is presently undergoing final environmental and integration tests at the Kennedy Space Center, with a launch slated for no earlier than mid-2025 atop the ULA Vulcan Centaur rocket. Subsequent NASA contracting decisions will most likely depend on Sierra Space's performance on these near-term CRS-2 missions. If such scenarios were indeed the case, would Dream Chaser be first in setting the paradigm for orbital cargo return, combining commercial innovation, shuttle-era capability, and 21st century reliability? EMI, acoustics, and day in the life. Before any space vehicle can be cleared for flight, it must pass a demanding series of qualification and environmental tests. For Dream Chaser and its first operational unit, Tenacity, this process has been especially rigorous due to the vehicle's novel design and intended reusability. Sierra Space has adopted a phased testing approach to validate both spacecraft integrity and performance under real-world launch and mission conditions. Each step of this testing gauntlet is vital to verifying that Dream Chaser will function reliably not just during launch and docking, but also through re-entry and runway landing, making sure nothing is left to chance. One of the first critical steps is electromagnetic interference and compatibility (EMI/EMC) testing. These tests are used to ensure that all of Dream Chaser's electronic systems can function properly without disrupting one another or being affected by the high levels of electromagnetic radiation common in both launch environments and spaceflight. given that a malfunctioning guidance or communication system could jeopardize an entire mission. Sierra Space performs EMI/EMC testing in highly controlled facilities to assess signal integrity, interference thresholds, and system shielding under extreme conditions. The multi-launcher strategy renders the Dream Chaser more resilient. It embodies all the important features, making it work eternally against delays, failures, or schedule conflicts arising from different rocket families. This means a far more reliable delivery cadence for NASA and other commercial partners, which can afford launch logistics changes without re-engineering the spacecraft. Unlike those, if something goes wrong stemming from the rocket supply chain or flight manifest problems that are tightly bound to proprietary launch systems, that vehicle will just have to sit and wait for an answer. As things stand, a spacecraft with an option to migrate anywhere in such a dynamic launch market is today's competitive advantage. The presence of the fairing affords further protection for the Dream Chaser configuration pre-launch, protecting it against debris or weather, something that cursed the shuttle's naked external tank. Protecting the thermal protection tiles against debris damage during ascent and smoothing coordination by making integration and test work easier at launch sites. In that perspective, this modular, flexible vision may serve as a prototype for next-generation spacecraft across the entire industry. If launch infrastructure is diversified, on account of Dream Chaser will ratchet up its utility in being a necessity over a novelty. Training doesn't begin in the sky, it's built from the ground up, where every second counts and every response is rehearsed to the edge of failure. Sierra plus NASA's coordinated training. As Dream Chaser approaches its inaugural mission to the International Space Station, ISS, Sierra Space and NASA have engaged in a robust joint training campaign designed to ensure mission readiness and safety at every level. These simulation-based rehearsals are critical in preparing the flight control teams for the vehicle's approach, capture, docking, and return. Operating from control centers in Louisville, Colorado, and NASA's Johnson Space Center in Houston, both teams have undergone extensive drills, often replicating the final 2 hours of flight operations. The goal? To refine communication, verify procedures, and rehearse critical decisions in real time under simulated pressure. The simulations place heavy emphasis on Dream Chaser's proximity operations with the ISS, a phase where precision, coordination, and redundancy are paramount. During this process, the spaceplane gradually closes in on the station and enters the approach ellipsoid, a protected zone that demands absolute accuracy. Using the station's Canadarm2 robotic arm, flight controllers simulate grappling Dream Chaser's shooting star module for berthing. Each scenario must pass through a series of stringent go-no-go checkpoints to ensure the safety of the uncrewed spaceplane and the human crew aboard the ISS. It is important to understand that these are not just another ordinary dry run. In fact, they are designed not only to stress the system, but to do so deliberately. A simulation, or overload training, is meant to render any number of failures, distractions, and unexpected challenges. These could involve anything from simulating loss of attitude control to subsystem malfunctions or delayed telemetry. These simulations will aid the teams in building situational awareness and being able to work on multiple issues concurrently, a very essential skill when seconds count. Under simulated conditions, operators are trained to stay calm while making decisions under pressure, as would be required in situations like those in commercial airline or military flight training. According to Sierra Space Flight Director Jerry Jason, a Shuttle and ISS mission veteran, this process teaches the body and mind to respond under stress. This simulation architecture is not just for inquiry procedural integrity, but also to validate Dream Chaser's flight rules, software, and ground support systems. Everything from docking operations to detaching and re-entering back into the atmosphere is assessed. These simulations serve as a systems check with full spectrum capability. They provide a controlled yet realistic environment to learn weaknesses and address them before launch. In full stride during preparations for its first flight, Sierra Space's rigorous joint training program is thus laying the operational foundations that ensure safe, reliable, and repeatable post-shuttle spaceplane missions. New Thermal Protection System. One of the most defining engineering features of Dream Chaser is its next-generation Thermal Protection System, TPS, which directly addresses many of the weaknesses that plagued the Space Shuttle. Unlike the Shuttle, which relied on approximately 24,000 fragile heat shield tiles, Dream Chaser uses a streamlined configuration of around 2,000 individually designed black and white tiles. These tiles are purpose-built for durability, reduced maintenance, and higher thermal efficiency. The use of larger 10x10-inch tiles compared to the Shuttle's 6x6-inch units means fewer seams, lower failure points, and simpler inspections between flights, essential traits for a truly reusable spaceplane. Sierra Space partnered with Oak Ridge National Laboratory to develop a proprietary silicon carbide-based material that significantly enhances thermal resilience. These advanced ceramic composite tiles are designed to withstand temperatures exceeding 300 degrees Fahrenheit, 1,700 degrees Celsius, while keeping the vehicle's internal structure well below operational limits. The new TPS incorporates a layered design where the outer shell handles extreme re-entry heat, while the inner section provides structural insulation. This not only increases survivability during atmospheric re-entry, but also reduces the risk of tile degradation over multiple missions, directly targeting one of the biggest cost and safety issues of the Shuttle era. White tiles are an innovation in addition to regular black tiles. While black tiles effectively radiate absorbed heat into their environment, white tiles reflect much more solar radiation, an important factor in temperature conditions while the vehicle is in orbit. This dual approach helps balance thermal loads, keeping the spacecraft and its cargo, especially sensitive scientific experiments, in stable conditions during the flight. Furthermore, tile bonding follows the process of utilizing RTV, room temperature vulcanizing, silicon, which has high-end performance when it comes to high heat performance and adhesion reliability, as opposed to previous adhesives used in the Shuttle program. Each tile with its adhesive bond undergoes extensive quality control, including mechanical pull testing to check the structural integrity. Whereas the heat shield of the Shuttle was rated for not more than 5 mission-per-year intervals, Dream Chaser has a target reuse rate of changing the tile set after involving it in about 15 missions before requiring a major refurbishment. It is this advance that leads to an economically scalable, reusable orbital vehicle. Thus, with reduced maintenance demand and improved lifespan for TPS, Sierra Space achieves not only an increase in mission cadence, but also future groundwork for a vehicle like Reverence to venture further and fly even more frequently. RP-1 and hydrogen peroxide system. Dream Chaser's propulsion system represents a notable divergence from the hypergolic fuels traditionally used in spacecraft like the Space Shuttle's orbital maneuvering system or the Apollo Command Module. Instead, Sierra Space has opted for a more modern and less hazardous solution, a combination of rocket propellant 1, RP-1, a highly refined kerosene, and hydrogen peroxide as the oxidizer. This choice prioritizes safety, ease of handling, and environmental responsibility, important considerations for a reusable spacecraft expected to operate frequently and reliably in the commercial spaceflight landscape. Hypergolic propellants ignite on contact, offering operational simplicity in vacuum, but at a high cost in toxicity and handling complexity. These fuels, such as hydrazine and nitrogen tetroxide, are extremely hazardous to humans and the environment, requiring strict safety protocols and specialized ground support equipment. By contrast, RP-1 and hydrogen peroxide are non-hypergolic and far less toxic, allowing for safer ground operations and lower overall risk to personnel. This aligns with Sierra Space's goal of building a reusable system with rapid turnaround potential. something that is hindered by the cleanup and inspections demanded by hypergolic use. At the functional level, the propulsion system of Dream Chaser, during several phases of missions, will support orbital maneuvering, attitude control, and burns for deorbit. These operations are critical to accurately approach the ISS and re-enter the atmosphere, especially due to the gliding runway landing profile. As part of the vehicle's qualification campaign, hot fire testing of the non-hypergolic engine system has been conducted to verify its performance and reliability under expected mission conditions. This gives assurance that the propulsion system is capable of working with the required consistency for ISS proximity operations and return trajectories. Another advantage for RP-1 hydrogen peroxide systems is the flexibility of mission parameters. As the combination can be made to scale in thrust and configuration, it provides a platform for incremental upgrades that might eventually accrue to support more demanding missions like extended duration orbital flights or even crewed variants of Dream Chaser. While precise performance metrics remain proprietary, the choice of using less hazardous and more manageable fuels suggests that a long-term operational strategy is geared towards scalability and sustainability. Might this fuel strategy be adopted as the standard for the next-generation reusable spaceplane? If safety, cost, and reusability are still paramount, Dream Chaser might become the one setting the trend. Reusability by design. A core objective of Dream Chaser's design philosophy is maximizing reusability, an area where previous winged spacecraft, notably the Space Shuttle, struggled to deliver on their full promise. While the Shuttle theoretically allowed for fast turnaround, in practice, each mission required extensive inspections, part replacements, and labor-intensive maintenance, particularly on the heat shield. Dream Chaser addresses this by targeting a mission cadence of up to 15 flights per vehicle before requiring major refurbishment, significantly outpacing the Shuttle's average of 5 missions per year. This advancement is a result of both material innovations and design streamlining aimed at operational efficiency. One of the most impactful changes contributing to this improvement is the reduction and optimization of thermal protection tiles. With approximately 2,000 black and white silicon carbide tiles, compared to the Shuttle's 24,000, Dream Chaser's system features larger and more resilient units that simplify inspections and minimize the chance of tile loss or failure. The reduced tile count not only lowers maintenance overhead, but also shortens the time needed between missions. Combined with modular access panels and exterior systems built with reusability in mind, Dream Chaser offers a maintenance profile more akin to modern aircraft than legacy space systems. Here we have integrated a design approach into almost all aspects of the vehicle, including the propulsion system, the landing gear, avionics, and thermal insulation that were engineered for long life and repeated utilization with minimum intervention. The Sierra Space model behind this reusability considers wear and tear cycles, thermal fatigue, and easy access for post-flight servicing, as opposed to the previous paradigm, whereby a vehicle could often need partial disassembly to get at those things after every flight. Dream Chaser reduces life cycle costs by integrating reuse into the architecture rather than retrofitting it, thus increasing commercial applicability. This method will finally be tested by judging how well these vehicles perform across many flights. At the 15 mission mark for each vehicle, Dream Chaser may turn space logistics economics on its head by making the cost per kilogram to low Earth orbit and beyond more feasible. Naturally, it's not just about cargo, because this is the model that will support future crewed versions and missions even farther into space. Dream Chaser's reusability-first design may mark a significant turning point in how orbiting vehicles are built, flown, and sustained, as this becomes a paramount consideration for the future of sustaining human presence on Earth. Another key factor in Dream Chaser's reusability is its departure from the all-or-nothing refurbishment model that hamstrung Shuttle-era operations. Sierra Space has deliberately designed the vehicle around modular subsystem components that can be swapped or upgraded independently without overhauling the entire craft. This compartmentalized maintenance strategy, common in commercial aviation but rare in space vehicles, means that turnaround time is no longer dictated by the slowest subsystem. For example, avionics or propulsion modules can be serviced or replaced without disturbing the rest of the spacecraft. This not only reduces downtime, but also enables iterative hardware improvements between flights, a concept often missing from legacy space platforms. Additionally, the landing gear and braking systems have been engineered with aircraft-grade servicing standards, including replaceable struts and wear-resistant materials rated for repeated runway use. If Dream Chaser performs as expected across multiple missions, this modular, service-friendly approach could become the blueprint for future orbital vehicles, prioritizing maintainability as much as performance in the age of rapid, reusable spaceflight. Scaling ambition beyond cargo demands more than hardware. It calls for trust, timing, and the courage to carry humans next. Preparing for human spaceflight. One of the most ambitious frontiers for Dream Chaser is its evolution from a cargo carrier to a crewed spaceplane. Sierra Space has long indicated that the vehicle's architecture was designed with human spaceflight in mind, even if the initial missions are uncrewed. A crewed variant, once certified, would restore a key capability not seen since the Space Shuttle era: the ability to return astronauts via a gliding runway landing. This could offer a smoother and more predictable re-entry experience compared to capsule splashdowns, potentially improving safety and post-flight recovery times for future astronauts. However, enabling human missions introduces new design and certification challenges. Sierra Space would need to integrate robust life support systems, pressure control, radiation shielding, and an abort mechanism, none of which are required for the cargo-only configuration. These adaptations would require NASA's human rating certification, a high bar for safety and reliability. Emergency escape during launch, in particular, poses a major engineering hurdle, especially for a winged vehicle mounted in a fairing atop a vertical rocket. Could this be addressed through a crew escape pod or a launch abort system integrated into the fairing itself? As a matter of fact, the company hinted at advanced versions of the spaceplane already in conceptual development. One such platform, publicly referred to as Reverence, is anticipated to build on the Dream Chaser design, but optimized specifically to carry humans. Although few technical details are made available, Reverence is most likely to feature upgraded avionics, larger pressurized volumes, and new abort systems that are meant to transport humans. One name alone strikes a chord with the Shuttle legacy, but signals Sierra Space's intent to take a different tack in commercial spaceflight tradition with innovation. Broader industry context raises interesting issues. If SpaceX's Crew Dragon eventually becomes the US's top crew carrier, will a built Dream Chaser accommodate missions in need of quicker access to runways and sensitive payloads? As NASA and its commercial partners stretch their gaze beyond low Earth orbits and set their sights on lunar and eventually deep space missions, a winged vehicle might fill an important niche in rapidly returning humans to Earth with high precision. It remains to be learned whether or not Dream Chaser or another vehicle from the same family is the right vehicle for that purpose, but it seems Sierra Space is preparing for competition. While Dream Chaser's cargo variant is paving the runway, the human-rated version will require not just new hardware, but an entirely different approach to risk. Beyond redundancy and shielding, every system must be built for crew survivability, including launch escape capability, an aspect historically easier to implement in capsules than in winged vehicles. Unlike Dragon, which uses integrated Super Draco thrusters for abort, Dream Chaser must rely on a separation and recovery strategy compatible with its fairing enclosed profile. Could we eventually see a detachable cockpit module or a fairing integrated abort motor? These are open questions NASA and Sierra Space must resolve before any astronaut boards the plane. If certified, a crewed Dream Chaser could serve not only as a ferry to the ISS, but as a rapid response return option for medical emergencies, time-critical samples, or future private space stations. Its gentle, horizontal landing could prove crucial for passengers unfit for ocean splashdowns or prolonged recovery times. In a scenario where microgravity lab work becomes commercially valuable or even medically essential, the ability to return people and experiments with surgical precision could become a differentiator. Dream Chaser's future isn't just about who it can carry, it's about how, where, and how fast it can bring them home. If you found this deep dive into NASA's next-gen spaceplane as fascinating as we did, don't forget to like, drop a comment with your thoughts, and subscribe for more future-focused aerospace breakdowns. Got questions or a hot take? We want to hear it. And don't go anywhere. Click on the next video on your screen to explore how Dream Chaser compares to SpaceX's Crew Dragon in crewed flight potential.